quest for a complete and consistent understanding of the universe has led to profound discoveries and persistent enigmas. Among the latter, the seemingly paradoxical nature of quantum entanglement and the implications of Bell's theorem stand as significant challenges to our classical intuitions about locality and realism. However, the 11-dimensional model, a theoretical framework that posits a reality extending far beyond our familiar 4 dimensions of spacetime, offers a compelling, albeit speculative, arena to re-examine these fundamental questions. By considering the possibility that our understanding of particles and their interactions has been inherently limited by our 4-dimensional perspective, we can explore how the 11-dimensional model might render the assumptions underlying Bell's theorem obsolete, opening new avenues for comprehending the non-local correlations of entanglement and the deeper nature of quantum reality. At the heart of the debate lies Bell's theorem, a pivotal result in quantum mechanics formulated by physicist John Stuart Bell in 1964. This theorem provides a rigorous mathematical framework for testing the validity of local hidden variable theories as an explanation for the correlations observed between entangled particles. Local hidden variable theories propose that the seemingly instantaneous connections between entangled particles are not due to any faster-than-light influence, but rather are predetermined by underlying local properties, the hidden variables, that the particles possess from the moment of their entanglement. Bell derived mathematical inequalities that must be satisfied by any theory adhering to both locality, the principle that an event is only directly influenced by its immediate surroundings and that no influence can travel faster than light, and realism, the assumption that particles have definite properties independent of measurement. The subsequent decades have witnessed numerous sophisticated experiments designed to test Bell's inequalities, and the overwhelming consensus of these experiments is that the inequalities are consistently violated. The correlations observed between entangled particles are stronger than any local realistic theory can accommodate. This experimental violation is widely interpreted by the physics community as compelling evidence for the inherent non-locality of quantum mechanics, suggesting that entangled particles are connected in a fundamental way that transcends our classical understanding of space and time, exhibiting correlations that cannot be explained by local influences or predetermined properties alone. However, the 11-dimensional model, a theoretical framework of the universe we inhabit, posits a universe with a far more intricate structure than our familiar 4-dimensional spacetime. This model suggests the existence of 3 primary dimensions, 10, 11, and 0, existing before, during, and after any other dimensions exist. From these primary dimensions of expansion, contraction, and the void springs forth all other dimensions of spacetime. 3 spatial dimensions, 1 through 3, as well as 6 temporal dimensions, 4 through 9. The primary dimensions provide the emergence necessary for the dimensions of what we call spacetime to exist at all. This provides for non-local relationships to develop between particles dynamically. Furthermore, as we have discussed, the 0, 10th, and 11th dimensions within this framework are often characterized as existing outside or transcending our conventional understanding of space and time. The 0 dimension represents pure potentiality, the 10th dimension, cosmic expansion, and the 11th dimension, cosmic contraction and interconnectedness. It is within this expanded multidimensional landscape that the assumptions underlying Bell's theorem, assumptions deeply rooted in our 4-dimensional experience, might be challenged. The very foundation of Bell's theorem rests upon the principle of locality within a 4-dimensional spacetime. It assumes that the properties of particles and the influences between them are constrained by the spatial and temporal separations we observe in our everyday reality. However, if reality operates within an 11-dimensional arena, the concept of distance and locality might be fundamentally different. The higher dimensions could provide pathways or connections between seemingly separated particles that are not constrained by the speed of light as it propagates through our three-dimensional space. Entangled particles, while separated in our three-dimensional world, might be connected through these higher dimensional shortcuts, rendering the notion of a local interaction insufficient to explain their correlated behavior. The 11th dimension in particular, with its role as the ultimate nexus of interconnectedness, could be the key to understanding this non-local link, providing a medium for instantaneous influence that bypasses the limitations of our four-dimensional spacetime. Furthermore, the 11-dimensional model might also prompt a re-evaluation of the assumption of realism, the idea that particles possess definite properties prior to measurement. If particles are not simply point-like entities residing in four-dimensional space, but are instead manifestations of more complex structures or dynamics within the higher dimensional fabric, perhaps vibrations or configurations within the expanded extra dimensions, then their observable properties in our four-dimensional world might be emergent and context-dependent. The act of measurement, an interaction confined to our limited four-dimensional perspective, could then be seen as the process that forces a projection of the particle's higher dimensional state onto our lower dimensional reality, seemingly creating a definite property where only a range of possibilities existed within the higher dimensional manifold. If entanglement arises from the fundamental interconnectedness of particles through the higher dimensions, particularly the 11th, then the instantaneous correlations observed might not require any faster-than-light communication within our four-dimensional space. Instead, the particles could be intrinsically linked at a deeper level of reality, their fates intertwined through a dimensional fabric that transcends our usual understanding of distance and time. The violation of Bell's inequalities, then, would not necessarily point to an inherently probabilistic universe or a breakdown of causality, but rather to the limitations of a theoretical framework that assumes a four-dimensional locality which might not be the fundamental architecture of reality. In conclusion, the 11-dimensional model, by extending the dimensionality of reality beyond our familiar four dimensions, offers a framework that challenges the direct applicability of Bell's theorem's conclusions about non-locality. The theorem's assumptions about particles existing and interacting solely within four-dimensional space-time, governed by a local realism, might be fundamentally incomplete if reality operates within a higher dimensional arena, where concepts of distance and time are redefined, and where interconnectedness transcends our lower dimensional perceptions. While Bell's theorem remains a mathematically valid result within its assumed framework, the 11-dimensional model suggests that these assumptions might be the very constraints that prevent us from fully comprehending the deeper, potentially deterministic, and interconnected nature of the quantum realm. The spooky action at a distance of entanglement could be a natural consequence of the interconnectedness inherent in a higher dimensional reality, rendering Bell's theorem, with its reliance on a limited four-dimensional perspective, a less definitive statement about the ultimate nature of the universe. Thank you for watching. If you enjoy the content on the 11-dimensional model channel, please like, subscribe, and share with a friend.